presentation. It's on efficient labeling of large data sets for NLP tasks. Now, hopefully today I'm going to show you that not only is data labeling a very necessary part of data science, but also that it can be quite interesting as well. So I'm going to talk you through the methodology I've used, labeling a large NLP data set. We're going to be looking at one specific task, and there's going to be a big focus on active learning and the idea of labeling smartly. So just to introduce myself, my name is Nichola, and I'm a data scientist at Connects One. So the first question a lot of people watching might have is, who are Connects One? Now, we're a business-to-business company, which is why you may not have heard of us. So we're a tech startup founded in 2012, and we provide call center dialer software. So one of our main selling features is that we're an omni-channel engagement platform. That means all different types of customer communication can be found in one place. And as a company, we've got a strong emphasis on AI features. And I've got a few facts here at the bottom. So we've got 300 plus call centers that use our software, and we handle 15 million different transactions every day. So here's some information about some of our customers and what kind of things they say about us. So some customers you might recognize, O2 and Gusto, and we cover all sorts of different domains. So we've got mobile phones, home improvements, health, debt collection, and life insurance, just to name a few of them. So Connects One is quite an up and coming company. Here are a few of our recent successes. So our latest investment round, we raised £93 million. We're the 6th fastest growing tech company in the north of the UK. And we've been touted as a potential unicorn, which is a company valued at £1 billion. We've also recently won Cloud Technology Provider of the Year. So like I said, we've got a strong focus on AI, and our AI is called Athena. Here are some of the tasks that Athena can currently do. So we've got sentiment analysis, entity recognition, automated call marking, just to give you some idea of what kind of information the clients can see. So we've got different agents, their sentiment has been tracked throughout their calls. The calls have also been scored against the scorecard, and they get points for different things. For example, giving a warm greeting or telling customers that calls are recorded. And my particular focus at Connects One is Athena Coach, which is an AI-based call center coach, which tracks the progress of calls in real time. And the goal is to detect key opportunities for the agent to improve the call outcomes. And these kind of opportunities could be an opportunity to upsell, an opportunity to overcome customer objections, or to respond appropriately to customer emotions. So we've got a very interesting AI project here, but like all data science projects, the key to success is good training data, and then more specifically, good labeled training data. So how do we collect or create training data for Athena Coach? So like we said, we've got 15 million transactions happening a day. We have millions and millions of call transcripts. We need to look through these and find and label the key opportunities in these past calls so that we can teach Athena Coach to detect them and then respond to them. So then this is the focus of today's presentation. We want to train Athena Coach to respond appropriately to customer frustration. Now, the first step to doing that is we need to label examples of customer frustrations within our data set. Now, some examples of customer frustration: you are stressing me out, I've had enough, I've been on hold for over an hour, this is ridiculous, or you didn't get back to me. So a few different labeling methodologies people could use. Most obvious, traditional supervised learning, which is hand labeling, where humans meticulously hand label every single example. The benefit of this is that you get very good labels, but as you can imagine, we've got millions and millions of calls. It's not going to be possible to label every single frustration in every call. And that's the case in many different examples. That is often just not possible to do traditional supervised learning. So what other options are out there? So there's a semi-supervised method where you can use rules and assumptions to label. The benefit is that it's low cost. The downside is that you do need explicit rules that underpin the data. So you can imagine we could think of some rules to label our frustrations. We could say, if the customer says they're frustrated, if the customer says they're annoyed, that is a frustration. But the way that people speak, it's just not going to be possible to make enough rules to cover every single example of customer frustration. So that one's not really an option to us. Another example might be weakly supervised learning, where you can use limited, noisy, or precise labels. Benefit again is that it's low cost, but you might not be getting that great labels. And like I said, we really want good labels for our Athena coach. So another option might be transfer learning, where you can use pre-trained models that you can find on the internet. Again, that's much lower cost than supervised learning. But downside is we need a model that understands how to label our specific data. So we might be very lucky, we might be able to find a model online that can label frustrations, but it might be trained on a specific data set. For example, it might be trained on Twitter. It doesn't mean it's going to translate well to our data set, which is call center data. So good labeled data is the key to a successful data science problem. We really don't want to compromise on this. Luckily, there is another option. There is active learning. This is where humans hand label specially selected examples. And these examples have been selected by some form of algorithm. And in fact, in our case, we're going to use active learning to create a model to learn how to label these frustrations. And then we're going to feed this model using weakly supervised learning to label all the millions of calls that we've got available to us. And that's what this presentation is going to be on, our methodology. So just to give you some more information on active learning, rather than humans labeling all the examples, we use a model which selects which examples humans should label. And these new labels feed back into the model to improve the model, which in turn leads to more efficient example selection for human labeling. And in the end, a better performing model with less labeled training data. So you can see in this figure in the right, at the top, we've got all the different samples. We've got green and red labels. And we want to train a model to learn to distinguish between the two labels. So the first sample in the middle, we can see that 28 different samples have been labeled at random. The model's tried to learn, but it's not done it's not done a very good job, really. And then the bottom diagram, we've labeled 28 samples again, but this time we've chosen which ones to label with active learning. And we can see we've got a much better performing model with the same number of labels. So as I've already mentioned, we've got 600 plus call centers, 50 million transactions a day. Even if we did use active learning and we're labeling smartly, we still can't manually label all the frustrations and all the calls. But we do want Athena Coach to cover all these different cases. So that's where the weekly supervised learning comes in. So we can use our gold standard labels, which is the labels the human has done, and then we can combine them with machine learning generated labels. We need to be aware that these machine learning labels have not been verified. They may be of worse quality, particularly on unseen domains. So here's a flow diagram describing the process. So we're going to start off with a subsample of the transcripts. We're going to do a keyword search, and we can look for keywords such as frustrated, annoyed, or some different swear words. We can find about 100 different label examples. That gives our machine learning models a good head start. So when we train our machine learning models, we get some samples out that we then label, feed back in to the machine learning models, and go round and round in this loop. Hopefully at some point we become happy with our machine learning model performance. And then we can use this to label all the rest of our call transcripts, combine them with the human labels, and get a fully labeled data set. So now we've gone through the process, how do we actually build these machine learning models? So the first thing to be aware of is that machine learning models don't understand words, and we need to turn these words into numbers. So there's two main techniques. First is bag of words, which are methods based on counting word frequencies. Second method is embeddings, where there is a vector representation of the meaning of a word or a sentence. So just to look at this in more detail, we've got a bag of words. The most commonly used bag of words technique is TF-IDF, which is term frequency inverse document frequency. I'm not going to go into too much detail, but you can see we've got some different utterances here, and you can see how those turn into some numbers. So the strengths are, it's very fast, it's very simple. The weaknesses are, it will not recognize words it's not seen before. And it will also not know how to link similar words. For instance, it won't know that frustrated is approximately equal to annoyed. So the other method was vector embeddings. So these do understand some kind of concept of meaning. They can be word-based or sentence-based. Some examples are word to vet, glove, or Bert. And in this work, I've used Bert sentence embeddings. So just to give you some context, this is the Bert sentence embedding for the sentence, I am frustrated. It's a 768 dimensional vector. And just to kind of show you how they understand the meaning of the sentences, I've calculated the similarity between some different sentences here and the sentence, I am frustrated. So we can see straight away that I'm annoyed, it thinks is 80% similar to I am frustrated, which is already a lot better than the TF-IDF. We can also see that I am not frustrated, it said is 74% similar, which I think is reasonable because the sentences are about the same kind of topic. The sentence structure is similar. It's only us in particular that care about whether the sentences are frustrated or not frustrated as our number one goal. We've got the neutral sentence, my house number is 17, which is 18% similar, it says. And then we've got a sentence, I've been on hold for over an hour, which it seems to think is more like a frustration than the neutral sentence. So this is looking quite promising. So which model should we use? So this work focuses on three main different types of models. We've got support vector machines, SVM. This is one of the most frequently used method in NLP. The strengths are it works well on small data sets, which is good because we're going to start off with a very small data set. It becomes less competitive on larger data sets when you get to hundreds of thousands of different training examples. So the next model is XGBoost, which is a tree-based model. It's the top method used in data science competitions. It's very good at learning patterns in data, but it's sometimes struggled to extrapolate patterns outside of its training range. And then the next method is a feed-forward neural network, which is the simplest form of neural network. It's good with nonlinear data, but it does need quite a lot of training data. So here we can see some example decision boundaries that each model has learned. So this is the sample data set. It's just a 2D data set. We've got red and blue points, and you can see that each model forms a slightly different decision boundary based on the training data. So you can see that each model is going to be putting forward different samples for us to label during active learning. So just for a bit of completeness, we've got some more cutting edge models to compare. So the first one is zero-shot learning, which is a pre-trained model that you can see on the internet. I put a link there if anyone wants to try this. So this returns a score for an input text against a given text label. The strength is you don't need any training examples, but then the negative is you can't give any training examples, so you can't get it to match your exact use case. So I've got an example here. I've given it a few sentences, asking it to score against the label frustration. So the first one, I've been on hold for over an hour. It thinks that's 95% of frustration, which is good. We've got the next sentence, I've just been paid recently, which is not really a frustration. It might be, but it's probably not a frustration, but it still thinks that's 80% of frustration. And then we've got the last example, give me your supervisor, buddy, give me your supervisor. And it thinks that's only 33% of frustration. So we can see it's doing okay, but it's just not really doing well enough to help speed up our labeling, I think. So the other example we've got is few-shot learning. Again, this is a pre-trained model. You can see the path here. So this learns a pattern from a few training examples, typically less than 5 training examples. So the strengths are you don't need very many training examples, but you can give it a little bit of guidance still. The downside is that it only performs well with common sense patterns and that it's painfully slow to run. For example, on my machine, it took 6 minutes to return an output for every single input. So I've got an example of this as well. So I read some guidance online of how to input the data. You can give it different sentences and then tell it how you would like to label. So I've given it some sentences, said emotion, frustration, emotion, not frustration. Then I've given it the sentence, I am happy, and it's returned the emotion happy, which is good because it's right, but it's not what we wanted because we wanted frustration or not frustration. So I tried again, tried to say frustration yes or frustration no. I asked it to label I am happy, and it returned a string of underscores, which is again not what we were looking for. So I'm sure I could get better results out of this if I tried, but I think we can see that it's probably not going to be a working tool for our active learning at this point. So we're just going to park these kind of models for now. We're not going to carry them on any further with our active learning. But I think into the future, maybe 5 or 10 years, these are going to be some of the models that we'll be using a lot more. So how do the models perform with active learning? So I've come up with a comparative task. How well can these models identify frustrations in a small data set? So I've come up with, I found one data set, one domain, 400 calls, 18,000 utterances. On average, there was one frustration every 100 utterances, which is quite high compared to a lot of different domains, which is why I've chosen this one to look at. So the method, start with labeling 100 initial utterances using the keyword search, train the models, label the 25 most likely frustrations from each model, and add these new labels into the training data for that model. Then we repeat this around and round. So the goal is find which models are best for active learning. So here we can compare the performance. So I'm just going to start by showing the random labeling, where we just label randomly selected samples. So we can see we've labeled nearly 1,400 utterances, and we've only found about 75 frustrations, so it's going very slow. Here's the total number of frustrations in our data set. We've just got slightly more than 1,000. If we were to randomly label, it would take about 18 days of human time to find and label every single frustration in the data set. So now we add on the embedding-based methods that have all performed very similarly to each other. So remember, we've got SVM, neural network, and XGBoost. So these start off very strong. They're returning about 80% frustrations on what they're selecting for us to label. And if we think at the beginning, they're going to be selecting the most obvious frustrations to us. And then as those are already labeled, the next ones are going to be slightly less obvious. So you can see that what it's selecting is getting less and less frustrations as we move on. The model will be learning a little bit better because it will have a bigger training set, but it's not been enough to compensate. So we can see that the lines are kind of leveling off before they find the total number of frustrations in the data set. Of course, they will eventually find all the frustrations in the data set, but it looks like it's going to take a while to find them all. So then we can add on some TF-IDF examples. So initially, these are returning about 50% frustrations for us to label, and we can see these are also tailing off as well. So even though none of the models have found all the frustrations within these labels themselves, when we combine them, they have actually found all the frustrations. And so this shows that we only need to label a few thousand utterances with active learning, which is 2 to 3 days of human time, which is a huge improvement on the 18 days that random labeling would take. But we can also see that these models are tending to converge on a particular decision boundary, and they're not finding all the frustrations quickly. So this slide is to compare the different training sets that each model has created to see how much overlap there is between them. So first, we're going to have a look at how many frustrations each model's found. So we can see the 2 TF-IDF models here, 3 embedding models. We can see the embedding models have found about 70% of the frustrations each. The TF-IDF have only found about 50%. So these new numbers I've added are the number of unique frustrations each model's found. So we can see each model has actually found some unique frustrations. And actually, the TF-IDF XGBoost has found 4% of the frustrations that no other model has found, which shows that even though the embedded models look like they're performing the best, there is still a lot that the TF-IDF models can contribute. So just adding the overlap between the different models here. And overall, this highlights the importance of compiling different methods and different models, because we need to maintain diversity during active learning. So what do we mean by diversity? So there are many different distinct types of frustration. For instance, my service is not working. I've been on hold for over an hour. You've taken a double payment, or the technician did not show up. Now in this figure on the right, I've tried to, so when we get the embeddings, we've got 760 8-dimensional vector, I've tried to condense this down into 2 dimensions so that we can view it on a graph, but you can imagine that the true representation of these utterances, each dot here is an utterance, that the true representation is a lot more complicated. So here we can see the grey dots are the not frustrations, the coloured dots are frustrations. So we can see there are some distinct pockets within this. So we've got the customers that are talking about payment problems, bad customer service, customers that are complaining they've been on the phone for too long and they're short of time, customers that are generally unhappy, and customers that are feeling pressured. So we can see that when we're training, we need to find all these different diverse types. So we need to keep our training data as diverse as possible, which means use a combination of models. And also we can keep a separate model for each domain. So for example, some of the domains I've looked at have got very polite customers, and it could be quite useful to keep these keep a training set separate so that we can look for politeness in different domains. So how to label? So there are quite a lot of different labeling tools out there. The one I've been using is Label Studio, which I definitely recommend. Strengths are that it's open source and that it allows for multiple labelers. It also allows for filtering and sorting by the prediction score. So you can see here I've got the different utterances that the customer and the agent say, and then I've got different scores based on each model, and we can sort and filter and choose what we're going to label based on this. We can also continuously train the model behind the scenes and feed back updated predictions to the human labelers. So in this case, we were labeling every single frustration, but do we need to do that in reality? When do we stop labeling, and when can we start switching to weekly supervised labeling and then label the rest of our data set with this method? So like I said, we don't need to label all examples. We can just select a stopping criteria. So you can see in this figure, this is a different data set. We've got 400,000 utterances across 10 different domains. And this active learning curve is how I've labeled it with active learning, trying to keep it diverse to use different models as much as possible. And this, as I was labeling, I was keeping track of the F1 score on a completely unseen set of call transcripts. And this test set needs to be manually labeled so that it's accurate, so we can really judge the performance on this test set. We can see that using active learning, we can see no real improvement beyond about 3,000 labels. So that seems like quite a good time to stop. We can see with the random labeling, even if we've done 10,000 labels, we'd only get an F1 score of 36%, which is significantly less than the active learning. Just to reinforce this point, we can see that 1,700 labels found by active learning is the same F1 score as 10,000 random labels. So this is our flow diagram that we saw before. So we're at this point, we've done the active learning, we've got our machine learning models, so we're on to the next step. We need to then label all the rest of our transcripts using weekly supervised learning. So hopefully we've got a good diverse training set, and we can focus more on the best performing models, but we still need to be very wary of the performance on unseen domains. So the method that we choose is dependent on our goals and our use case, and there's a balance between false positives and false negatives when we're labeling our data set. This is the age-old data science problem of precision versus recall. So like I said before, we can compare the model performance on a completely unseen set of calls. This test set needs to be representative of all the other calls within the label, and it also needs to be manually labeled so that we know that the labels are accurate. Now, just to remind people, precision is the percentage of utterances that are true frustrations. Recall is the percentage of true frustrations found. And as we saw throughout this presentation, the models return a score based on how certain they are it's a frustration, or maybe more precisely, how much it matches the frustrations in their training set. So we can choose a certain threshold for this score. So for example, 0.5, and we say anything above 0.5, we're going to label a frustration. Anything less than 0.5, we're not going to label a frustration. And that will give us a particular precision and recall score. And if we change this threshold, for example, if we say that an utterance has to have a score higher than 0.9 instead, and we label things higher than 0.9 as a frustration, we're going to see that our labels for frustration are going to be a lot more accurate. Our precision is going to be higher, but we won't have labeled that many of the frustrations, so the recall will be much lower. And that's hopefully, you can see this in this graph to the right. So you can see this bottom right-hand side of the graph, we've got quite a high threshold. So this is so we're only going to be labeling frustrations on the ones it's most certain about. So precision is going to be high, but the recall is low. It's not actually labeled that many of the frustrations. As we lower the threshold, we go up the graph till we get to the point where the threshold is at 0. So everything is labeled a frustration. We've found every single frustration. So the recall is 1, but the precision is very, very low. So just to compare the different models on this graph, so we've got the embeddings SVM, the embeddings neural network, embeddings XGBoost, and the TF-IDF SVM. And the higher up the line, the better performing the model. So we can see our best performing model are the embeddings model, in particular, this SVM embeddings model. So when we want to label the rest of our data set, if we remember we're doing weekly supervised learning, we can choose a particular cutoff point on the precision recall curve. So for example, if we wanted to get 80% precision on our labels, we can choose 80% precision here. And if we read it off, we'd get 34% recall. And then we can use this point to label all the rest of the data. So you see here that this was a threshold score of 0.7. So anything higher than 0.7, we label frustration. Anything lower than 0.7, we label not frustration. So once we've labeled all the data, we've got to our goal, which is a fully labeled data set. So for this example, I've chosen 80% precision, which might not sound particularly, well, it sounds high, but it might not sound like it's very accurate, but I can say that the embeddings models have done very well at learning frustrations. And actually the ones that is incorrect at this kind of level of confidence are very borderline cases. And for our particular use case, I'd much rather have a very high precision and low recall, so that I know that the things that are labeled frustrations are very likely to be frustrations. It doesn't matter so much that I've only found 34% of the frustrations. So we're coming to the end of my presentation. So as a summary, I've presented our approach for labeling, which is active learning coupled with weekly supervised learning. And this leads to a huge reduction in labeling time compared to random labeling. I've also shown it's very important to keep diversity in the machine learning prediction by using an ensemble of models, and that you can track performance during active learning and choose the stopping criteria. But you do also need to remain wary when transferring labels with weekly supervised learning, because they're not always going to be accurate and you need to be careful on unseen domains. So thank you for listening to my presentation.